So hello everyone and welcome to NEETOPEDIA, that is NEET ka encyclopedia. I hope you are enjoying all the audiobooks given on this channel. And today we are going to start with another audiobook of chemistry, that is S block elements. So let's get started. Unit 10, the S block elements. The first element of alkali and alkaline earth metals differ in many respects from the other members of the group. The S block elements of the periodic table are those in which the last electron enters the outermost s orbital. As the s orbital can accommodate only 2 electrons, 2 groups belong to the S block of the periodic table. Group 1 of the periodic table consists of the elements lithium, sodium, potassium, rubidium, cesium and francium. They are collectively known as the alkali metals. These are so called because they form hydroxides on reaction with water which are strongly alkaline in nature. The elements of group 2 include beryllium, magnesium, calcium, strontium, barium and radium. These elements, with the exception of beryllium, are commonly known as the alkaline earth metals. These are so called because among the alkali metals, sodium and potassium are abundant, and lithium, rubidium and cesium have much lower abundances. Francium is highly radioactive. Its longest lived isotope, francium-223, has half-life of only 21 minutes. Of the alkaline earth metals, calcium and magnesium rank 5th and 6th in abundance respectively in the Earth's crust. Strontium and barium have much lower abundances. Beryllium is rare and radium is the rarest of all, comprising only 10 to the power minus 10% of igneous rocks. The general electronic configuration of the S block elements is noble gas Ns1 for alkali metals and noble gas Ns2 for alks. Lithium and beryllium, the first elements of group 1 and 2 respectively, exhibit some properties which are different from those of the other members of the respective group. These anomalous properties, they resemble the second element of the following group. Thus, lithium shows similarities to magnesium and beryllium to aluminium in many of their properties. This type of diagonal similarities is commonly referred to as diagonal relationship in the periodic table. The diagonal relationship is due to the similarity of ionic sizes and/or the charges to radius ratio of the elements. Monovalent sodium and potassium ions and divalent calcium and magnesium ions are found in large proportions in important biological functions such as maintenance of ion balance and nerve impulse conduction. 10.1 Group 1 Elements, the alkali metals. The alkali metals show regular trends in the physical and chemical properties with the increasing atomic number. The atomic and chemical properties of alkali metals are discussed below. 10.1.1 Electronic configuration. All alkali metals have one valence electron, that is Ns1, outside the noble gas core. The loosely held s electron in the outermost valence shell of these elements makes them the most electropositive metals. They readily lose electrons to give monovalent M+ ions. Hence, they are never found in free state in nature. 10.1.2 Atomic and ionic radii. The alkali metals have the largest sizes in a particular period of the periodic table. With increase in the atomic number, the atom becomes larger. The monovalent ions are smaller than the parent atom. Atomic and ionic radii of the alkali metals increase on moving down the group, that is, they increase in size while going from lithium to cesium. 10.1.3 Ionization enthalpy. The ionization enthalpies of the alkali metals are considerably low and decrease down the group from lithium to cesium. This is because the effect of increasing size outweighs the increasing nuclear charge, and the outermost electron is very well screened from the nuclear charge. 10.1.4 Hydration enthalpy. The hydration enthalpies of the alkali metal ions decrease with increase in ionic sizes. That is, Li plus is greater than Na plus is greater than K plus is greater than Rb plus is greater than Cs plus. Li plus has maximum degree of hydration, and for this reason lithium salts are mostly hydrated. For example, LiCl 10.1.5 physical properties. All the alkali metals are silvery white, soft and light metals. Because of the large size, these elements have low density, which increases down the group from lithium to cesium. However, potassium is lighter than sodium. The melting and boiling points of the alkali metals are low, indicating weak metallic bonding due to the presence of only a single valence electron in them. The alkali metals and their salts impart characteristic color to an oxidizing flame. This is because the heat from the flame excites the outermost orbital electron to a higher energy level. When the excited electron comes back to the ground state, there is an emission of radiation in visible region of the spectrum, given below. Crimson red color, sodium yellow, potassium violet, rubidium red-violet and cesium blue. Alkali metals can therefore be detected by their respective flame test and can be determined by flame photometry or atomic absorption spectroscopy. These elements, when irradiated by light, the light energy absorbed may be sufficient to make an atom lose electron. This property makes cesium and potassium useful as electrodes in photoelectric cells. 10.1.6 Chemical properties. The alkali metals are highly reactive due to their large size and low ionization enthalpy. The reactivity of these metals increases down the group. Number 1. Reactivity towards air. The alkali metals tarnish in dry air due to the formation of their oxides, which in turn react with moisture to form hydroxides. They burn vigorously in oxygen, forming oxides. Lithium forms monoxides, sodium forms peroxide, and other metals form superoxides. The superoxide O2- ion is stable only in the presence of large cations such as potassium, rubidium, and cesium. In all these oxides, the oxidation state of the alkali metal is millimeters are normally. Number 2. Reactivity towards water. The alkali metals react with water to form hydroxide and dihydrogen. It may be noted that although lithium has most negative electrode potential value, its reaction with water is less vigorous than that of sodium, which has least negative E0 value among the alkali metals. This behavior of lithium is attributed to its small size and very high hydration energy. Other metals of the group react explosively with water. They also react with proton donors such as alcohol, gaseous ammonia, and alkynes. Number 3. Reactivity towards dihydrogen. The alkali metals react with dihydrogen at about 673 Kelvin to form hydrides. All the alkali metal hydrides are ionic solids with high melting points. Number 4. Reactivity towards halogens. The alkali metals react vigorously with halogens to form ionic halides. However, lithium halides are somewhat covalent. This is because of the high polarization capability of lithium ion. The lithium ion is very small in size and has tendency to distort electron cloud around the negative halide ion. Since an ion with large size can be easily distorted among halides, lithium iodide is the most covalent in nature. Number 4. Reducing nature. The alkali metals are strong reducing agents, lithium being the most and sodium being the least powerful. The standard electron potential E0, which measures the reducing power, represents the overall change. With the small size of its ion, lithium has the highest hydration enthalpy, which accounts for its high negative E0 value and its reducing power. I'm skipping problem 10.2 for you to solve it later, or you can pause the video and solve it right now. Number 6. Solutions in liquid ammonia. The alkali metals dissolve in liquid ammonia, giving deep blue solutions which are conducting in nature. The blue color of the solution is due to the ammoniated electron, which absorbs energy in the visible region of light and thus imparts blue color to the solution. The solutions are paramagnetic and on standing slowly liberate hydrogen, resulting in the formation of amide. In concentrated solution, the blue color changes to bronze color and becomes diamagnetic. 10.1.7 Uses. Lithium metal is used to make useful alloys. For example, lithium to make white metal bearings for motor engines, with aluminium to make aircraft parts, and with magnesium to make armor plates. It is used in thermonuclear reactions. Lithium is also used to make electrochemical cells. Sodium is used to make a sodium-lead alloy to make PbEt4 and PbMe4. These organolead compounds were earlier used as anti-knock additives to petrol, but nowadays vehicles use lead-free petrol. Liquid sodium metal is used as coolant in fast breeder nuclear reactions. Potassium has a vital role in biological systems. Potassium chloride is used as fertilizer. Potassium hydroxide is used in manufacture of soft soap. It is also used as an excellent absorbent of carbon dioxide. Cesium is used in devising photoelectric cells. 10.2 General characteristics of the compounds of alkali metals. All the common compounds of the alkali metals are generally ionic in nature. General characteristics of some of their compounds are discussed here. 10.2.1 Oxides and hydroxides. On combustion in excess of air, lithium forms mainly the oxide Li2O. Sodium forms the peroxide Na2O2, while potassium, rubidium and cesium form the superoxides MO2. Under appropriate conditions, pure compounds M2O, M2O2 and MO2 may be prepared. The increasing stability of peroxide or superoxide as the side of the metal ion increases is due to the stabilization of large ions by larger cations due to lattice energy effects. These oxides are easily hydrolyzed by water to form hydroxides according to the following reactions. M2O plus water gives 2M plus 2OH minus. M2O2 plus 2 water molecule gives 2M plus 2OH minus plus H2O2. 2MO2 plus 2H2O gives 2M plus 2OH minus plus H2O2 plus O2. The oxides and the peroxides are colorless when pure, but the superoxides are yellow or orange in color. The superoxides are also paramagnetic. Sodium peroxide is widely used as an oxidizing agent in inorganic chemistry. Problem 10.3 Why is Ko2 paramagnetic? Solution: the superoxide O2- is paramagnetic because of one unpaired electron in antibonding 2p molecular orbital. The hydroxides, which are obtained by the reaction of oxides with water, are all white crystalline solids. The alkali metal hydroxides are the strongest of all bases and dissolve freely in water with evolution of much heat on account of these intense hydration. 10.2.2 Halides. The alkali metal halides are all high melting colorless crystalline solids. They can be prepared by reaction of the appropriate oxide, hydroxide or carbonate with aqueous hydrohalic acid. All of these halides have high negative enthalpies of formation. The del F H0 values for fluorides become less negative as we go down the group, while the reverse is true for del F H0 for chlorides, bromides and iodides. For a given metal, del F H0 always becomes less negative from fluoride to iodide. The melting and boiling point always follows the trend: fluoride is greater than chloride, is greater than bromide, is greater than iodide. All these halides are soluble in water. The low solubility of LiF in water is due to its high lattice enthalpy, whereas the low solubility of CSI is due to its smaller hydration enthalpy of these two ions. Other halides of lithium are soluble in ethanol, acetone and ethyl acetate. LiCl is soluble in pyridine also. 10.2.3 Salts of oxoacids. Oxoacids are those in which the acidic proton is on the hydroxyl group with an oxo group attached to the same atom. Example: carbonic acid, sulfuric acid. The alkali metals form salts with all the oxoacids. They are generally soluble in water and thermally stable. Their carbonates M2CO3 and in most cases the hydrogen carbonates MHCO3 are also highly stable to heat. All the electropositive character increases down the group. the stability of the carbonates and hydrogen carbonates increases. Lithium carbonate is not so stable to heat. Lithium, being very small in size, polarizes a large carbonate ion. It does not exist as a solid. 10.3 Anomalous properties of lithium. The anomalous behavior of lithium is due to exceptionally small size of its atom and ion, high polarizing power. As a result, there is increased covalent character of lithium compound, which is responsible for the solubility in organic solvents. Further, lithium shows diagonal relationship to magnesium, which has been discussed subsequently. 10.3.1 Points of difference between lithium and other alkali metals. Number 1. Lithium is much harder. Its melting point and boiling point are higher than other alkali metals. Number 2. Lithium is least reactive but the strongest reducing agent among all the alkali metals. On combustion in air, it forms mainly monoxides, Li2O, and nitride, Li3N, unlike other alkali metals. Number 3. LiCl is deliquescent and crystallizes as a hydrate, LiCl.2H2O, whereas other alkali metal chlorides do not form hydrates. Number 4. Lithium hydrogen carbonate is not obtained in the solid form, while all other elements form solid hydrogen carbonates. Number 5. Lithium, unlike early metals, form no ethanide on reaction with ethine. Number 6. Lithium nitrate, when heated, gives lithium oxide Li2O, whereas other alkali metals nitrate decompose to give the corresponding nitrite. 4LiNO3 gives 2Li2O plus 4NO2 plus O2, and 2NaNO3 gives 2NaNO2 plus O2. Number 7. LiF and Li2O are comparatively much less soluble in water than the corresponding compounds of other alkali metals. 10.3.2 Points of similarities between lithium and magnesium. The similarity between lithium and magnesium is particularly striking and arises because of their similar sizes. Atomic radii, lithium is equal to 152 picometer, of magnesium is equal to 160 picometer, while ionic radii of Li plus is equal to 76 picometer and Mg2 plus is equal to 72 picometer. The main points of similarity are: Number 1. Both lithium and magnesium are harder and lighter than other elements in their respective groups. Number 2. Lithium and magnesium react slowly with water. Their oxides and hydroxides are much less soluble, and their hydroxides decompose on heating. Both form a nitride Li3N and Mg3N2 by direct combination with nitrogen. Number 3. The oxides Li2O and MgO do not combine with excess oxygen to give any superoxide. Number 4. The carbonates of lithium and magnesium decompose easily on heating to form oxides and CO2. Solid hydrogen carbonates are not formed by lithium and magnesium. Number 5. Both LiCl and MgCl2 are soluble in ethanol. Number 6. Both LiCl and MgCl2 are deliquescent and crystallize. 10.4 Some important compounds of sodium. Industrially important compounds of sodium include sodium carbonate, sodium hydroxide, sodium chloride, and sodium bicarbonate. The large-scale production of these compounds and their uses are described below. Sodium carbonate or washing soda, Na2CO3.10H2O. Sodium carbonate is generally prepared by solvate process. In this process, advantage is taken of the low solubility of sodium hydrogen carbonate, whereby it gets precipitated in the reaction of sodium chloride with ammonium hydrogen carbonate. The latter is prepared by passing CO2 to a concentrated solution of sodium chloride saturated with ammonia, where ammonium carbonate followed by ammonium hydrogen carbonate are formed. The equations for the complete process may be written as 2NH3 plus water plus carbon dioxide gives ammonium carbonate, and ammonium carbonate plus water plus sodium dioxide gives 2 ammonium hydrogen carbonate. Ammonium hydrogen carbonate plus NaCl, and these are heated to give sodium carbonate. 2NaHCO3 gives Na2CO3 plus 2CO2 plus H2O. In this process, ammonia is recovered when the solution containing NH4Cl is treated with CaOH whole twice. Calcium chloride is obtained as a byproduct. 2NH4Cl plus CaOH whole twice gives 2NH3 plus CaCl2 plus H2O. It may be mentioned here that Solvay process cannot be extended to manufacture of potassium carbonate because potassium hydrogen carbonate is too soluble to be precipitated by addition of ammonium hydrogen carbonate to a saturated solution of potassium chloride. Properties. Sodium carbonate is a white crystalline solid which exists as decahydrate, that is Na2CO3.10H2O. This is also called washing soda. It is readily soluble in water and on heating the decahydrate loses its water of crystallization to form monohydrate. Above 373 Kelvin, the monohydrate becomes completely anhydrous and changes to a white powder called soda ash. Carbonate part of sodium carbonate gets hydrolyzed by water to form an alkaline solution. Uses. Number 1. It is used in water softening, laundering and cleaning. Number 2. It is used in manufacture of glass, soap, borax and caustic soda. Number 3. It is used in paper, paints and textile industries. Number 4. It is an important laboratory reagent both in quantitative and qualitative analysis. Sodium chloride NaCl. The most abundant source of sodium chloride is seawater, which contains 2.7 to 2.9% by mass of the salt. In tropical countries like India, common salt is generally obtained by evaporation of seawater. Approximately 50 lakh tons of salt are produced annually in India by solar evaporation. Crude sodium chloride, generally obtained by crystallization of brine solution, contains sodium sulfate, calcium chloride and magnesium chloride as impurities. Calcium chloride and magnesium chloride are impurities because they are deliquescent. To obtain pure sodium chloride, the crude salt is dissolved in minimum amount of water and filtered to remove insoluble impurities. The solution is then saturated with hydrogen chloride gas. Crystals of pure sodium chloride separates out. Calcium and magnesium chloride, being more soluble than sodium chloride, remain in the solution. Sodium chloride melts at 1081 Kelvin. It has a solubility of 36 gram in 100 gram of water at 273 Kelvin. The solubility does not increase appreciably with the increase in temperature. Uses. Number 1. It is used as common salt or table salt for domestic purpose. Number 2. It is used for the preparation of Na2O2 and NaOH and Na2CO3. Sodium hydroxide or caustic soda, NaOH. Sodium hydroxide is generally prepared commercially by the electrolysis of sodium chloride in Kastner-Kellner cell. A brine solution is electrolyzed using a mercury cathode and a carbon anode. Sodium metal discharged at the cathode combines with mercury to form a sodium amalgam. Chlorine gas is evolved at the anode. The amalgam is treated with water to give sodium hydroxide and hydrogen gas. That is 2Na amalgam plus 2H2O gives 2NaOH plus 2Hg plus H2. Sodium hydroxide is white, translucent solid. It melts at 591 Kelvin. It is readily soluble in water to give a strong alkaline solution. Crystals of sodium hydroxide are deliquescent. The sodium hydroxide solution at the surface reacts with the CO2 in the atmosphere to form Na2CO3. Uses. Number 1. In the manufacture of soap, paper, artificial silk and a number of chemicals. Number 2. In petroleum refining. Number 3. In the purification of bauxite. Number 4. In the textile industries for processing cotton fabrics. Number 5. For the preparation of pure fats and oils. Number 6. As a laboratory reagent. Sodium hydrogen carbonate or baking soda, NaHCO3. Sodium hydrogen carbonate is known as baking soda because of its decomposition on heating to generate bubbles of carbon dioxide. Sodium hydrogen carbonate is made by saturating a solution of sodium carbonate with carbon dioxide. The white crystalline powder of sodium hydrogen carbonate, being less soluble, gets separated out. Na2CO3 plus H2O plus CO2 gives 2NaHCO3. Sodium hydrogen carbonate is a mild antiseptic for skin infections. It is used in fire extinguishers. 10.5 Biological importance of sodium and potassium. A typical 70 kg man contains about 90 gram of sodium and 170 gram of potassium, compared with only 5 gram of iron and 0.06 gram of copper. Sodium ions are found primarily on the outside of cells, being located in blood plasma and in the interstitial fluid which surrounds the cells. These ions participate in transmission of nerve signals, in regulating the flow of water across cell membranes, and in the transport of sugars and amino acids into the cells. Sodium and potassium, although so similar chemically, differ quantitatively in their ability to penetrate cell membranes, in their transport mechanisms, and in their efficiency to activate enzymes. Thus, potassium ions are the most abundant cations within cell fluids, where they activate many enzymes, participate in oxidation of glucose to produce ATP, and with sodium are responsible for the transmission of nerve signals. There is a very considerable variation in the potassium ions found on the opposite sides of the cell membranes. As a typical example, in blood plasma, sodium is present to an extent of 143 millimole per liter, whereas the potassium level is only 5 millimole per liter within the red blood cells. These concentrations change to 10 millimole per liter and 105 millimole per liter. These ionic gradients demonstrate that a discriminatory mechanism called the sodium-potassium pump operates across the cell membrane, which consumes more than 1/3 of the ATP used by the resting animal and about 15 gram per 24 hour in a resting human. 10.6 Group 2 elements. Alkaline earth metals. The group 2 elements comprise beryllium, magnesium, calcium, strontium, barium and radium. They follow alkali metals in a periodic table. These, except beryllium, are known as alkaline earth metals. The first element, beryllium, differs from the rest of the members and shows diagonal relationship with aluminium. The atomic and physical properties of the alkaline earth metals are shown in table 10.2. 10.6.1 Electronic configuration. These elements have 2 electrons in the s orbital of the valence shell. Their general electronic configuration may be represented as noble gas Ns2, while alkali metals, the compounds of these elements, are also predominantly ionic. 10.6.2 Atomic and ionic radii. The atomic and ionic radii of the alkaline earth metals are smaller than those of the corresponding alkali metals in the same periods. This is due to the increased nuclear charge in these elements. Within the group, the atomic and ionic radii increase with the increase in the atomic number. 10.6.3 Ionization enthalpies. The alkaline earth metals have low ionization enthalpy due to fairly large size of the atoms. Since the atomic size increases down the group, their ionization enthalpy decreases. The first ionization enthalpy of the alkaline earth metals are higher than those of the corresponding group 1 elements. This is due to their small size as compared to the corresponding alkali metals. This is interesting to note that the second ionization enthalpies of the alkaline earth metals are smaller than those of the corresponding alkali metals. 10.6.4 Hydration enthalpies. Like alkali metal ions, the hydration enthalpies of alkaline earth metal ions decrease with increase in ionic size down the group. That is, beryllium ion is greater than magnesium ion, is greater than calcium ion, is greater than strontium ion, is greater than barium ion. The hydration enthalpies of the alkaline earth metals ions are larger than those of the alkali metal ions. Thus, compounds of alkaline earth metals are more extensively hydrated than those of the alkali metals. Example, MgCl2 and CaCl2 exist as MgCl2.6H2O and CaCl2.6H2, while NaCl and KCl do not form such hydrates. 10.6.5 Physical properties. The alkaline earth metals in general are silvery, white, lustrous and relatively soft but harder than alkali metals. Beryllium and magnesium appear to be somewhat greyish. The melting and boiling points of these metals are higher than corresponding alkali metals due to smaller sizes. The trend is, however, not systematic. Because of the low ionization enthalpies, they are strongly electropositive in nature. The electropositive character increases down the group from beryllium to barium. Calcium, strontium and barium impart characteristic brick red, crimson and apple green colors respectively to the flame. In flame, the electrons are excited to a higher energy levels, and when they drop back to the ground state, energy is emitted in the form of visible light. The electrons in beryllium and magnesium are too strongly bound to get excited by flame. Hence, these elements do not impart any color to the flame. The flame test for calcium, strontium and barium is helpful in the detection in qualitative analysis and estimation by flame photometry. The alkaline earth metals, like those of alkali metals, have high electrical and thermal conductivities, which are typical characteristics of metals. 10.6.6 Chemical properties. Number 1. Reactivity towards air and water. Beryllium and magnesium are kinetically inert to oxygen and water because of the formation of an oxide film on their surface. However, powdered beryllium turns brilliantly on ignition in air to give BeO and Be3N2. Magnesium is more electropositive and burns with dazzling brilliance in air to give MgO and Mg3N2. Calcium, strontium and barium are readily attacked by air to form the oxide and nitride. They also react with water with increasing vigor even in cold to form hydroxides. Number 2. Reactivity towards halogens. All the alkaline earth metals combine with halogen at elevated temperature, forming their halides. The thermal decomposition of NH4 whole twice BeF4 is the best route for preparation of BeF2, and BeCl2 is conveniently made from the oxide. BeO plus C plus Cl2 at 600 to 800 Kelvin gives BeCl2 plus CO. Number 3. Reactivity towards hydrogen. All the elements except beryllium combine with hydrogen upon heating to form their hydrides, MH2. BeH2, however, can be prepared by the reaction of BeCl2 with LiAlH4. 2BeCl2 plus LiAlH4 gives 2BeH2 plus LiCl plus AlCl3. Number 4. Reactivity towards acid. The alkaline earth metals readily react with acids, liberating dihydrogen. M plus 2HCl gives MCl2 plus H2. Number 5. Reducing power or reducing nature. Like alkali metals, the alkaline earth metals are strong reducing agents. This is indicated by the large negative values of their reduction potentials. However, their reducing power is less than those of the corresponding alkali metals. Beryllium has less negative value compared to other alkaline earth metals. However, its reducing nature is due to the large hydration energy associated with the small size of beryllium ion and relatively large value of the atomization enthalpy of the metal. Number 6. Solutions in liquid ammonia. Like alkali metals, the alkaline earth metals dissolve in liquid ammonia to give deep blue-black solution, forming ammoniated ions. From this solution, the ammoniates, that is MnH3 2 plus, can be removed. 10.6.7 Uses. Beryllium is used in the manufacture of alloys. Copper beryllium alloys are used in preparation of high-strength springs. Metallic beryllium is used for making windows of X-ray tubes. Magnesium forms alloys with aluminium, zinc, manganese and tin. Magnesium-aluminium alloys, being light in mass, are used in aircraft construction. Magnesium is used in flash powders and bulbs, incendiary bombs and signals. The suspension of magnesium in hydroxide in water, called mixed of magnesia, is used as an antacid in medicine. Magnesium carbonate is an ingredient of toothpaste. Calcium is used in extraction of metals from oxides, which is difficult to reduce with carbon. Calcium and barium metals, owning their reactivity with oxygen and hydrogen at elevated temperatures, have often been used to remove air from vacuum tubes. Radium salts are used in radiotherapy, for example, in the treatment of cancer. 10.7 General characteristics of compounds of the alkaline earth metals. The di-positive oxidation state is the predominant valence of group 2 elements. The alkaline earth metals form compounds which are predominantly ionic but less ionic than the corresponding compounds of the alkali metals. This is due to increased nuclear charge and smaller size. The oxides and other compounds of beryllium and magnesium are more covalent than those formed by heavier and large-sized members. The general characteristics of some of the compounds of alkali earth metals are described below. Number 1. Oxides and hydroxides. The alkaline earth metals burn in oxygen to form the monoxide MO, which except for BeO have rock salt structure. The BeO is essentially covalent in nature. The enthalpies of formation of these oxides are quite high and consequently they are very stable to heat. BeO is amphoteric while oxides of other elements are ionic in nature. All these oxides except BeO are basic in nature and react with water to form sparingly soluble hydroxides. The solubility, thermal stability and the basic character of these hydroxides increase with increasing atomic number from MgOH whole twice to BaOH whole twice. The alkaline earth metal hydroxides are however less basic and less stable than alkali metal hydroxides. Beryllium hydroxide is amphoteric in nature as it reacts with acid and alkali both. Number 2. Halides. Except for beryllium halides, all other halides of alkaline earth metals are ionic in nature. Beryllium halides are essentially covalent and soluble in organic solvents. Beryllium chloride is a chain structure in solid state as shown below. In the vapor phase, BeCl2 tends to form chloro-bridged dimer which dissociates to form linear monomer at high temperatures of order of 1200 Kelvin. The tendency to form halide hydrates gradually decreases. For example, MgCl2.HH2O, CaCl2.6H2O, CrCl2.6H2O and BaCl2.2H2O. The hydration of the hydrated chlorides, bromides and iodides of calcium, strontium and barium can be achieved on heating. However, the corresponding hydrated halides of beryllium and magnesium on heating further hydrolysis. The fluorides are relatively less soluble than the chlorides owing to their high. Number 3. Salts of oxoacids. The alkaline earth metals also form salts of oxoacids. Some of these are carbonates. Carbonates of alkaline earth metals are insoluble in water and can be precipitated by addition of sodium or ammonium carbonate solution to a solution of a soluble salt of these metals. The solubility of carbonates in water decreases as the atomic number of the metal ion increases. All the carbonates decompose on heating to give carbon dioxide and the oxide. Beryllium carbonate is unstable and can be kept only in the atmosphere of CO2. The thermal stability increases with the increasing cationic size. Sulfates. The sulfates of the alkaline earth metals are all white solids and stable to heat. BeSO4 and MgSO4 are readily soluble in water. The solubility decreases from CaSO4 to BaSO4. The greater hydration enthalpies of Be2+ and Mg2+ ions overcome the lattice enthalpy factor and therefore their sulfates are soluble in water. Nitrates. The nitrates are made by the dissolution of the carbonates in dilute nitric acid. Magnesium nitrate crystals with 6 molecules of water, whereas barium nitrate crystallizes as anhydrous salt. This again shows a decreasing tendency to form hydrates. With increasing size and decreasing hydration enthalpy, all of them decompose on heating to. Problem 10.4. Why does the solubility of alkaline earth metals hydroxide in water increase down the group? Solution. Among alkaline earth metal hydroxides, the anion being common, the cationic radius will influence the lattice enthalpy. Since lattice enthalpy decreases much more than the hydration enthalpy with increasing ionic size, the solubility increases as we go down the group. Problem 10.5. Why does the solubility of alkaline earth metal carbonates and sulfates in water decrease down the group? Solution. The size of anions being much larger compared to the cations, the lattice enthalpy will remain almost constant within a particular group. Since the hydration enthalpies decrease down the group, solubility will decrease as found for alkaline earth metal carbonates and sulfates. 10.8 Anomalous behavior of beryllium. Beryllium, the first member of the group 2 metals, shows anomalous behavior as compared to magnesium and rest of the members. Further, it shows diagonal relationship to aluminium, which is discussed subsequently. Number 1. Beryllium has exceptionally small atomic and ionic size and thus cannot compare well with other members of the group. Because of high ionization enthalpy and small size, it forms compounds which are largely covalent and get easily hydrolyzed. Number 2. Beryllium does not exhibit coordination number more than 4, as in its valence shell there are only 4 orbitals. The remaining members of the group can have a coordination number of 6 by making use of d orbitals. Number 3. The oxide and hydroxide of beryllium, unlike the hydroxides of other elements in the group, are amphoteric in nature. 10.8.1 Diagonal relationship between beryllium and aluminium. The ionic radius of beryllium ion is estimated to be 31 picometer. The charges to radius ratio is nearly the same as that of aluminium ion. Since beryllium resembles aluminium in some ways, some of these similarities are: Number 1. Like aluminium, beryllium is not readily attacked by acids because of the presence of an oxide film on the surface of the metal. Number 2. Beryllium hydroxide dissolves in excess of alkali to give a berylate ion, just as aluminium hydroxide gives aluminate ion. Number 3. The chlorides of both beryllium and aluminium have Cl- bridged chloride structure in vapor phase. Both the chlorides are soluble in organic solvents and are strong Lewis acids. They are used as Friedel-Crafts and catalysts. Number 4. Beryllium and aluminium ions have strong tendency to form complexes, that is BeF42-, AlF63-. 10.9 Some important compounds of calcium. Important compounds of calcium are calcium oxide, calcium hydroxide, calcium sulfate, calcium carbonate, and cement. These are industrially important compounds. The large-scale preparation of these compounds and their uses are described below. Calcium oxide or quicklime, CaO. It is prepared on a commercial scale by heating limestone, that is CaCO3, in a rotatory kiln at 1070 to 1270 Kelvin. CaCO3 when heated gives CaO plus CO2. The carbon dioxide is removed as soon as it is produced to enable the reaction to proceed to completion. Calcium oxide is white amorphous solid. It has a melting point of 2870 Kelvin. On exposure to atmosphere, it absorbs moisture and carbon dioxide. The addition of limited amount of water breaks the lump of lime. This is called the slaking of lime. Quick lime slaked with baking gives solid soda lime. Being a basic oxide, it combines with acidic oxide at high temperatures. CaO plus SiO2 gives CaSiO3. 6CaO plus P4O10 gives 2Ca3PO4 whole twice. Uses. Number 1. It is an important primary material for manufacturing cement and is the cheapest form of alkali. Number 2. It is used in the manufacture of sodium carbonate from caustic soda. Number 3. It is employed in the purification of sugar and in the manufacture of dyestuffs. Calcium hydroxide, slaked lime, or CaOH whole twice. Calcium hydroxide is prepared by adding water to quicklime, CaO. It is a white amorphous powder. It is sparingly soluble in water. The aqueous solution is known as lime water, and a suspension of slaked lime in water is known as milk of lime. When carbon dioxide is passed through lime water, it turns milky due to the formation of calcium carbonate. CaOH whole twice plus CO2 gives CaCO3 plus H2O. On passing excess of carbon dioxide, the precipitate dissolves to form calcium hydrogen carbonate. CaCO3 plus CO2 plus H2O gives CaHCO3 whole twice. Milk of lime reacts with chlorine to form hypochlorite, a constituent of bleaching powder. 2CaOH whole twice plus 2Cl2 gives CaCl2 plus CaOCl2 plus 2H2O. Uses: Number 1. It is used in the preparation of mortar, a building material. Number 2. It is used in whitewash due to its disinfectant nature. Number 3. It is used in glass making, in tanning industry for the preparation of bleaching powder and for purification of sugar. Calcium carbonate CaCO3. Calcium carbonate occurs in nature in several forms like limestone, chalk, marble, etc. It can be prepared by passing carbon dioxide through slaked lime or by the addition of sodium carbonate to calcium chloride. CaOH whole twice plus CO2 gives CaCO3 plus H2O. CaCl2 plus Na2CO3 gives CaCO3 plus 2NaCl. Excess of carbon dioxide should be avoided since this leads to the formation of water-soluble calcium hydrogen carbonate. Calcium carbonate is a white fluffy powder. It is almost insoluble in water. When heated to 1200 Kelvin, it decomposes to evolve carbon dioxide. CaCO3 at 1200 Kelvin gives CaO plus CO2. It reacts with dilute acid to liberate carbon dioxide. CaCO3 plus 2HCl gives CaCl2 plus H2O plus CO2. CaCO3 plus H2SO4 gives CaSO4 plus H2O plus CO2. Uses: It is used as a building material in the form of marble and in the manufacture of quicklime. Calcium carbonate along with magnesium carbonate is used as a flux in the extraction of metals such as iron. Specially precipitated CaCO3 is extensively used in the manufacture of high-quality paper. It is also used as an antacid, mild abrasive in toothpaste, a constituent of a chewing gum, and a filler in cosmetics. Calcium sulfate or plaster of Paris or CaSO4.5H2O. It is a hemihydrate of calcium sulfate. It is obtained when gypsum, that is CaSO4.2H2O, is heated to 393 Kelvin. Above 393 Kelvin, no water of crystallization is left and anhydrous calcium sulfate is formed. This is known as dead burnt plaster. It has a remarkable property of setting with water. On mixing with adequate quantity of water, it forms a plastic mass that gets into a hard solid in 5 to 15 minutes. Uses: The largest use of plaster of Paris is in the building industry as well as plasters. It is used for immobilizing the affected part of organ where there is a bone fracture or sprain. It is also employed in dentistry, in ornamental work, and for making cast of statues and busts. Cement. Cement is an important building material. It was first introduced in England in 1824 by Joseph Aspdin. It is also called Portland cement because it resembles with the natural limestone quarried in the Isles of Portland, England. Cement is the product obtained by combining materials rich in lime, CaO, with other materials such as clay, which contains silica, SiO2, along with oxides of aluminium, iron, and magnesium. The average composition of Portland cement is CaO 50 to 60%, SiO2 20 to 25%, Al2CO3 5 to 10%, MgO 2 to 3%, Fe2O3 1 to 2%, and SO3 1 to 2%. For a good quality cement, the ratio of silica to alumina should be between 2.5 and 4. The ratio of lime to total of the oxides of silicon, aluminium, and iron should be as close as possible to 2. The raw materials for the manufacture of cement and limestone are clay. When clay and lime are strongly heated together, they fuse and react to form cement clinker. This clinker is mixed with 2 to 3% by weight of gypsum to form cement. Thus, important ingredients present in Portland cement are dicalcium silicate 20%, tricalcium silicate 51%, and tricalcium aluminate 11%. Setting of cement. When mixed with water, the setting of cement takes place to give a hard mass. This is due to the hydration of molecules of the constituents and their rearrangement. The process of adding gypsum is only to slow down the process of setting of cement so that it gets sufficiently hardened. Uses. Cement has become a commodity of national necessity for any country next to iron and steel. It is used in concrete and reinforced concrete, in plastering, and in the construction of bridges, dams, and buildings. 10.10 Biological importance of calcium and magnesium. An adult body contains about 25% of magnesium and 1200 grams of calcium, compared with only 5 grams of iron and 0.06 grams of copper. The daily requirement in human body has been estimated to be 200 to 300 milligrams. All enzymes that utilize ATP in phosphate transfer require magnesium as the cofactor. The main pigment for absorption of light in plants is chlorophyll, which contains magnesium. About 99% of body calcium is present in bones and teeth. It also plays an important role in neuromuscular function, interneural transition, cell membrane integrity, and blood coagulation. The calcium concentration in plasma is regulated at about 100 mg per liter. It is maintained by two hormones, calcitonin and parathyroid hormone. Do you know how that bone is not an inert and unchanging substance, but is continuously being solubilized and redeposited to the extent of 400 mg per day in a man? All this calcium. Summary. The S block elements of the periodic table constitutes group 1 and group 2. They are so called because their oxides and hydroxides are alkaline in nature. The alkaline metals are characterized by 1 s electron, and the alkaline earth metals has 2 s electron in the valence shell of their atoms. These are highly reactive metals forming monopositive and diapositive ions respectively. There is a regular trend in the physical and chemical properties of the alkali metals with increasing atomic numbers. The atomic and ionic sizes increases, the ionic enthalpies decrease systematically down the group. Somewhat similar trends are observed among the properties of alkaline earth metals. The first element in each of these groups, lithium in group 1 and beryllium in group 2, shows similarities in properties with second member of the next group. Such similarities are termed as diagonal relationship in the periodic table. As such, these elements are anomalous and as far as their group characteristics are concerned. The alkali metals are silvery white, soft, and low melting. They are highly reactive and soluble in water, forming strong alkalis. Important compounds of sodium include sodium carbonate, sodium chloride, sodium hydroxide, and sodium hydrogen carbonate. Sodium hydroxide is manufactured by Kastner-Kellner process and sodium carbonate by Solvay process. The chemistry of alkaline earth metals is very much like that of alkali metals. However, some differences arise because of reduced atomic and ionic sizes and increased cationic charges. In case of alkaline earth metals, the oxides and hydroxides are less basic than alkali metal oxides and hydroxides. Industrially, important compounds of calcium include